Scheme design is about developing practical ideas from concept design. It provides alternative solutions before detailed design is carried out. In scheme design, we go one step further in performing initial design checks on steel members, including slabs, beams, columns, trusses, and bracing. In this tutorial, you will learn scheme design of a medium-rise steel building. This is the last part of 30-part series on steel design. If you are a civil or structural engineer or a civil engineering student looking to enhance your understanding of scheme and concept design, this tutorial is for you. Hey friends, if you're new here, I'm Dr. Qureshi, a senior lecturer in structural engineering and design at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. Concept and scheme design is divided into these 4 lectures and tutorials. Scheme design worked example is the 4th and final part of concept and scheme design. In this tutorial, I will be developing a scheme design for a medium-rise steel building. Before I go through steps for scheme design, I would like to cover what did we do in concept design. This was the building footprint which was given to us, and we came up with primary and secondary beam configuration, 2 bracings, 4 shear walls. The grid size was 6 by 12. We came up with these member sizes. So for secondary beam, we had this beam and S275 steel. For primary beam, we have this beam, S275 steel. For columns, we had UKC 254, S355 steel, and slab was composite slab with ComFloor 60 steel deck. And then we have scheme design. For scheme design, we have these steps. So first loading, and then slabs, and then beams, and then columns, and then other members. Now this is very important when we have to work out loading. We will know how do we work out loading, where do these loads come from. The first thing is loading. So before we work out loading, we have to work out fire rating. The building height is 14 meter and assume no sprinklers are used, and it is office. Fire rating is 60 minutes. So first establish the fire rating and then design loads. The self weight is to be calculated. Allow 1.5 or 1 kilonewton per meter for finishes. The total dead load will be, excluding weight of the slab because we have not decided about the slab, is 1.5 kilonewton. Live loads allow 1 kilonewton per meter for movable partitions. For offices, we normally use 2.5 kilonewton per meter square. Simply add this up. This will give you 3.5 kilonewton per meter square as live load. So the total load will be 1.5 plus 3.5. This is unfactored at the moment. The next step is design of slab. Now design of slab means that I go to load span table of this particular supplier, ComFloor 60 load span table. So our slab span is 2 meter, fire resistance is 60, and total load is 5 kilonewton per meter square. So I am choosing this 120 mm deep slab which can span up to 3.5 meter. My span of slab is 2 meters. So it means that this is fine. If my span was say 4 meter, then I cannot use this. So can I say that I want to use this ComFloor 120 mm deep slab with 0.9 mm deck and A142 mesh? Now remember that in loading, I just have to work out self weight of the slab. All other loads are with me. Now if you go to load span tables of ComFloor 60, you will see that if you're using 0.9 millimeter thick sheeting, its weight is 0.1 kilonewton per meter square. This is the weight of the sheet. Concrete volume is 0.008 meter cube per meter square. If we multiply this volume with the density 25 kilonewton per meter cube, now this will give me weight of the concrete. Now the total weight of the slab is going to be the weight of the sheeting plus weight of concrete. This will give me 2.3. All I have to do is to add up this weight into earlier weight. So dead loads are 2.3 for the composite slab. This is the self weight. Allow for steel work weight of beams 0.5 kilonewton, so that I don't have to revise these sections. So 0.5 for steel work. Finishes I already assumed 1.5. So if I add these things up, it will give me 4.3 kilonewton per meter square.
The live load, on the other hand, will remain the same. Assume roof load is the same for other floors. Now here, for simplicity, I'm assuming that roof load is same for all other floors, but normally roof load will have lesser live loads. For ULS, for ultimate limit state, we will multiply this load with 1.35 and 1.5 live load. In total, you will get 11.1 kilonewton per meter square. So from here, I will work out loading on secondary beams. First, span of secondary beam is 12 meter. Load on secondary beam is equal to half width from each beam side. Now this width, this is 2 meter, this is 2 meter, this is 2 meter. So if I'm talking about this, this is 1 and this is half slab width from each beam side. So from the top and from the bottom, I will have 2 meters. So that's the reason it is 2 meters. So load on secondary beam will be equal to half width from each side multiplied with the load. 4.3 times 2. Now this will give me load in kilonewton per meter because load is distributed from the slab to the beam. And same is the case with the live load. I will multiply it with 2. What will you multiply load with for this beam D23? Now the concept is really simple because this beam is taking load from both sides of the slab and this beam is taking only one side of the slab. For ULS ultimate limit state, again I'm using factored load times 2. The factored load was here. W is the load and then L is the length. We get this 399.6 kilonewton meter. Shear force is going to be half on both sides. How do I design secondary beam? For this, I will have to add this dead plus live load. This is giving me 15.6. This is unfactored load. Now, in the UK, according to Eurocode, we should only use the live load. But the design practice in the UK is that we use both unfactored dead plus live load when we are trying to work out the deflection. So for secondary beams, we will simply check its deflection, and from that deflection equation, we will work out I. The deflection limit, which is the most common one, is span over 360. Span is 1200 and 360 comes from the formula. So this is the maximum deflection that this beam can deflect. Now for UDL, I have this formula. Now in this formula, if I make I as my subject, then it will be 5WL power 4 over 384E into delta. W is this load, unfactored load. Length is given 384. E is modulus of elasticity, which is 210 gigapascal. And delta is 33. From here, if you put all these values, you get this value, 60,779. The beam that we have chosen earlier, we have to see that what is its I. If you go to Tata Steel Blue Book again, 533210101, its I is 61500. So our chosen section has got second moment of area and major axis as 61500, which is higher than required. We can say that this beam is going to be fine in deflection. And usually for secondary beams, if the secondary beams work fine for SLS, normally it will work fine for ULS. The only thing you need to check here is the deflection for secondary beams. Similar checks can be done for grid lines A or D. The beams have half load of the internal beams, but these beams also support weight of facade. So these outside beams have half of the load of internal beams, but they support weight of the facades. It is common practice to make these beams same size. Secondary beams are acting on primary beams as point loads. Reaction from this and this has to be added. So the reaction earlier was 133.2 from secondary beam. So that reaction has to be multiplied by 2, because if I have 2 point loads, the formula for its moment is PL over 3. Shear force is going to be equal to only P. This is your moment. These are the checks that we will need for ultimate limit state. This is a primary beam. In primary beams, normally we check buckling. Assume S275 steel and the beam is plastic, and assume value of C1 equal to 1.35. So our chosen section earlier that we chose was 610229 into 123 for 6 meter, and for C1 value, because we have point load, so C1 is going to be 1.35. The capacity is 626, which is higher than applied moment. This means that the primary beam is fine. The section that we chose is fine. If it is not fine, then we can go to the higher section, we can revise it. Now, if primary beam works for ULS, then it normally works for deflection. So deflection is going to be fine. So don't worry about deflection. Similar checks can be done for beams on grid 1 and 4. So these beams have half load of internal beams, but these beams also support weight of facade. And again, it's a common practice to make these beams the same size. Loads on columns. Now there are two ways in which you can work out loads on columns. And the easiest way is to work out the tributary area. So I will just go half of this beam, half of this beam, and half of this beam, and half of this beam. This will give me area 12 by 6. Okay, this column is supporting area 12 by 6, which is equal to 72 meters square. This is termed as tributary area. For ULS, the loading is 11.1 kilonewton per meter square. If you multiply this ULS loading with 72 and with 4 floors, you will get total load on ground floor column. Now there is one caveat here, which is that here we are assuming that roof will have the same loading. Normally roof will have lesser loading. It will have half of the loading of other floors. But here, for simplicity, we are assuming roof will have the same load. So this is the easiest way with the help of tributary area. So alternatively, load can be obtained from beam reactions. So column supports 2 secondary beams and 2 primary beams, as I mentioned. And using S355 steel, assuming a buckling reduction factor of 0.6 for a tall floor, 0.6 times 355, it will give me allowable stress of 213. I will simply use axial stress is equal to axial force divided by area. And I have this allowable stress. So area is equal to axial force over axial stress. So axial force is the force in column, converting it into newtons, divided by allowable area, which is here. So this will give me area of the column. So for my chosen column, the area, again, you will find this area in Tata Steel Blue Book 254,254,167. This area is 213 centimeters square. The area is greater than the area required. This section is okay. Similar checks can be done for grid lines A and D and 1 and 4. But load on these columns can be found out by working out tributary area. So for example, load on this column B4 is going to be half of the column in C2. Or if I wanted loading on column over here, the corner one, its loading is going to be even less than that. The edge and corner columns also support weight of facade, and the columns are part of braces as well, which can take wind load. The next thing for me is to work out wind loading. So wind on short face is resisted by shear walls. So assume wind load of 0.8 kilonewton per meter square. Normally you would work out this loading based on various factors, based on wind speed, based on terrain, based on various other factors. Normally it is in between 0.8 to 1.2 kilonewton per meter square. So we have assumed it as 0.8 kilonewton per meter square. You can assume it as 1 as well. So area of the short face is 14 by 18. You multiply this wind load with the area, you get total wind load. And this is split equally between 4 shear walls. So that's why you divide it by 4. So on each wall, you will have 50 kilonewton load. Again, wind on long face is resisted by bracing. So area of long face is 36 by 14. In the same way, you will work out area of long face, then multiplied with the wind load, you will get 403. Now this is resisted by 2 braces, 201 kilonewton on each brace because it's divided by 2. Then we have to work out loading on each level. Because wind is a variable load, so that's why we multiplied with 1.5. So the total load is going to be 302 kilonewton. I will start from roof. Roof is taking portion from the floor at the bottom. So that's why we multiplied with 0.5. The height is 3.5 times 3 times the total load, which is 302, divided by overall height of the building. So this will give me portion of the wind load resisted by roof, which is here. At second and third level, which is here and here, you can see that this is resisting loading half from top and half from bottom. So 1.5 times 1.5, 1.5 plus 1.5, it is 3 times total load divided by height of building. This will give me load at level 3 and 4. At level first, the situation is different. Level first, this is half of 3, which is 1.5, and then half of 5 meter, which is 2.5. It means it is 4. So this load at first floor is resisting 1.5 meter from the top and 2.5 from the bottom. So that's why I have multiplied 0.5 with top and bottom height multiplied by total load divided by story height. This is giving me load on level 1. And at ground level, this is supporting only this 2.5 meter. So simply you multiply 0.5 times 5 or 2.5 with the total load divided by 14. This will give you load at the ground floor level. The next thing is to work out notional horizontal loads. Previously, they used to be termed as notional horizontal loads. Now we term it as equivalent horizontal loads. These are used to represent frame imperfections. Steel frames will always have some kind of imperfection. And these are normally 1 over 200 of your vertical load, 0.5% or 1 over 200 of your vertical load. Area of level 1 is 18 by 36. You multiply it with the ULS load. This will give you total load. Total load on a floor. If you multiply it with 1 over 200 or 0.5%, it will give you 36 kilonewton. Now this is equally split between two braces per flow level. At ground level, we don't have it because we don't have any flow. And then we add up the equivalent horizontal force with the wind force. So the total load at ground is going to be 374.4 kilonewton. Now force and wind brace. Now this is very important to understand that we use X bracing. So we ignore the member in compression. We assume that only tension members contribute to lateral stability. So if wind is blowing in this direction, only the bracing which is dark is taking part. The one in dotted is taking compression. So its tensile resistance is 0. And if wind blows in the other direction, you can see that this bracing, it is dotted now. So we have to ignore the compression. So we design bracing as tension member. So other members work when wind blows from other direction. Total vertical component, we find out the vertical component in bracing, which is 312 using simple trigonometry. This is to be added to the column vertical load due to gravity in design of columns. So in design of columns, we have to add this load. And the resultant force in this bracing at the bottom is going to be this vertical component plus horizontal component, which is here. The resultant force in your bracing is going to be 487 kilonewton. Once we have this resultant force, assume S275 steel, brace in tension, stress is equal to force over area, area is equal to force over stress. Stress is 275. From here, you work out required area. And now you can use a flat plate as well. But here I have used equal leg angles, 100 by 100 into 12, for which area is 2270. You can find out this from Tata Steel Blue Book. So its area is greater than the required one. So this is fine. So bracing is fine. This is how you design bracing. And then we have other members. I will move on to trusses now. At roof level, we are providing truss. Assume that it is required to create a large column free space at the upper level. At upper level, for example, if we require large column free space, the primary beam is efficient up to 12 meter. The long spans are often achieved using trusses. Now the span is 18 meter and then it is supporting loading. The gray side, you can see that how it's supporting loading. So consider parallel chord roof truss. This is the span to depth ratio. For 18 meter, we are assuming 1.8 meter. Let us say we are using a depth of 1.3 meter. Just interpolate between these two maximum. Obviously, you cannot use this. Your truss is not 100 meter. Just use higher than 500. Because this is 20 meters, so probably use 1 meter or more than 1 meter. Now, idealize this truss as a beam. Again, load on the truss. It is taking half the slab width from each side of the truss, which means it's going to be 12. So from here it is 6, and then from here to here it is 6. Then dead load. Now here I'm assuming it to be the same. Normally this load is going to be lower. So this is taking this much load by multiplying it with 12. Again, live load is going to be small as well, but here for simplicity we have assumed that it's taking the same live load. So multiply ULS, the total floor load, times 12, it will give me 133.2 kilonewton per meter, which is quite heavy load. And then moment, you can see that it is 5,394 and shear is 1190. It's so heavy. We work out dead plus live without factors. Deflection limit is a span over 360, which is 50. So again, using 5WL power 4 or 384 EI for UDL, we make I as the subject. Then from here, we work out 1.22 to 10 raised power 10 millimeter power 4. Now this is our I value. Now this bending stiffness is provided by top and bottom chord, like the flange in the beam. And the diagonal members, they provide the shear capacity, like web in a beam. Now simplify I is equal to A into D square over 2 from parallel axis theorem, where assuming top and bottom chords have area A, I is equal to AD square over 2. From here, I can say that I is equal to 2I over D square. 2 times I have just found out. D is the depth of the truss. The required I is going to be 14438. It should be millimeter power 4. Truss chords are usually square or rectangular hollow sections. So we're using SHS 355 by 12. And again, in the same way, find out from section table, the provided area is greater than required. The depth is to the center of the chords. Truss total depth is going to be 1300 plus 350. So the total depth is going to be 1650 millimeter. Verify that chords are adequate for ULS. Force in the top flange compression is equal to force in the bottom flange, which means that the bending moment is equal to force into depth. So force is equal to bending moment divided by depth. So bending moment is given, divided by depth is 1.3. So force is 4149. Now stress is equal to force over area. So once we have force, we divide this force over area of the provided section. So this is giving us 248.5 Newton per millimeter square. This is certainly higher than this value. So stress should not exceed. Now yield stress in tension is this much. Now reduced stress in compression will be due to buckling. Assume reduction to be 0.8. This will have tension at the bottom and this will have compression at the top. So compression chords will have reduction. So that's why we're multiplying it with 0.8. So this is giving me 284. The section is still adequate in both tension and compression. So we checked its serviceability, we checked its strength. So the section is going to be fine. The diagonal is a shear. Assume angle of diagonal as 45. So vertical component is equal to shear force. The vertical component is equal to force in the diagonal times sine 45. So from here we can work out force in diagonal, which is 1695. Stress is equal to force over area. The stress should not exceed the allowable compression stress, which is 284, which we found out a little earlier. So force over stress, this will give us area. Try this section, 200 by 200 into 10, which is providing 7,490, which is greater than required. It means that the diagonal members are fine as well. And then we have other consideration. We have stability analysis, alpha crate connections, beam to column, beam to beam braces, column bases and foundations, RC shear walls, how to avoid progressive collapse in accidental loading, and then drawings.